My name is Simon Brand. I'm here to talk to you today about how to write well-behaved value wrappers. I work for Microsoft on the Visual C++ team. I'm their developer advocate, so the idea is if you have any questions about Visual C++, Visual Studio for C++, Visual Studio Code, VC package, come talk to me. That's what I'm here for. Something about this presentation, please ask questions. I will be covering some reasonably advanced topics here, and not everyone in the room will have all the necessary context. So if you want me to spend a bit more time on a code sample, explain something, please just raise your hand and ask. It's better that I explain because there'll be other people who don't know too. So please just ask questions. They should be interactive. First, I should talk a bit about, when I say value wrappers, what do I mean? Like, what specifically am I talking about? So one definition I could have is types with value semantics which can store objects of any type. This is kind of nebulous description, but some examples would be std optional, std pair. You might be familiar with Jonathan Beccara's named type library for his strong type blog posts and talks which he gives. So these are all examples. You have a value, you copy it, you copy the wrapper, that means you copy the value. You move the wrapper, you move the value. They kind of act like ints. This is a common phrase you might have heard. Do like the ints do. And that's essentially what value semantics is. So these are what I'm talking about today. Well-behaved. So I want to tell you how to write well-behaved value wrappers. And there are two criteria which I'm interested in. The first is something which hopefully as C++ programmers we all care about. We write C++ because we want our code to be performant, fast. We don't want to be paying additional runtime overhead that we don't have to. Okay, make sense? For the other one, here's a quote you may or may not have heard. If a feature is accidentally misapplied by the user and causes what appears to them to be an unpredictable result, then that has a high astonishment factor and is therefore undesirable. So this is sometimes referred to as the principle of least astonishment or of least surprise. Put more succinctly, I want our code to be unsurprising. I don't want our type to act in ways where you try and compile it, you get a weird error, what's going on? Even worse, you run your program, it gives you the wrong result. This is surprising behavior, and I do not want this. So performant, unsurprising. That's what I care about in this talk. This is a cautionary tale. This is a comment which I found in a code base which probably a lot of us have used today. This is a very large project, and it says, GCC has missed optimizations with maybe, which is the type this is a comment for, in the past, and may generate extra branches or loads or stores. Use with caution on hot paths, because it's no longer known, it's still not known whether this is a problem. So essentially what the people who did this, who wrote this code did, is they have not watched this talk yet. Because if they had watched this talk, then they would know what's causing all of these problems, what things they need to care about, how they need to optimize, how they make their code not generate all of these extra branches and loads and stores and whatnot. So hopefully by the end of this talk, you could go and look at this code base and say, oh, they didn't apply this thing that Simon talked about, or they didn't think about this aspect of their type design. So that's my goal for this. I'll start off with something that hopefully we're all familiar with, comparison operators. We like to be able to compare one object to another. So this is about the simplest value wrapper I could think of. It's called wrapper. It takes a template parameter and then stores an instance of that type in the wrapper. Hopefully this makes sense to you. Now one thing we might want to do is if we say we have a wrapper of ints, we might want to compare them. but this does not compile. And this makes sense. Like we have ints, we like to be able to compare them. If we have a wrapper of ints, maybe we want to compare these as well. There's some times where you might not want this, and sometimes where you might. It's something you have to at least consider. So maybe in a lot of cases, this is surprising behavior. We tried to do some operation which seemed reasonable and it didn't compile. Why? Well, because we didn't define those operators. So we could go ahead and define them. And maybe it looks something like this. These are all the comparison operators which one has to write if you're implementing std optional. I don't expect you to be able to read this, just know it's a lot of code. I mean, you can do things like implement some in terms of others and whatnot, but when it comes down to it, fundamentally, you have to write all of these overloads. Otherwise, someone's going to try and compare less than and it'll work, and then they'll try and compare greater than and it'll compiler error or something. Like, that's surprising. We don't want this. So, I mean, this works. Like, our code now compiles. It's fine. So we are unsurprising. This is a win. But it's a lot of code. Like, we don't want to write this. We don't want to maintain it. It's a lot of noise. So maybe we can do better. Has anyone seen this? Lego Movie? Yeah, great film. I've watched it like at least 30 times because my 4-year-old is obsessed with this film. My favorite character in the Lego Movie is this guy. He loves his spaceships. And his spaceships look like this. And in C++20, we have spaceships too. They don't look quite like this, though. They look more like this. So if you're not familiar with this, this is the spaceship operator or the three-way comparison operator. And you might be familiar with it from other languages. I think Ruby has this. Plenty of other languages have some kind of analog to this. It's kind of like a string comparison. Like you have an expression which will return something less than 0 if A was less than B. It will return something greater than 0 if A is greater than B, and something equal to 0 if they're equal or equivalent. This equal equivalent thing is like an entire talk on its own, so I don't really want to get into that, but just note there's some nuance here. This is kind of the basic idea of the spaceship operator. You don't generally write it yourself, but this is how it's specified, and you'll see how it becomes useful. Does this all make sense to everyone? Cool. So say we have a pair type. It's not standard pair. It's just it has a T and a U, and it stores them. It's very, very simple. What we can do is write equals default. Isn't this so cool? We just say, I want a spaceship operator which is going to compare my pairs. And it just works. This will perform a lexicographical comparison of our types dependent on the ordering of our members. So this will compare T, and then it will compare U. And we don't have to write anything else. We just write equals default, and it works. If you're wondering what this does under the hood, it generates code something like this. So you can see it's kind of doing a comparison on T, and then if it doesn't already know if it's less than or greater than, then it goes on and does a comparison against U. The return type looks awful because C++ essentially has to work out like what's the common type between all of these, because they might return strong orderings or weak orderings. Because we don't just return an int. No, that would be like C code. No, we return something a lot more complex. If you want to know more about spaceship operator, you can come talk to me later or go and look at the CPP reference page. It's really, really interesting stuff. But now we can take our optional comparison operators, which we had earlier, and with the power of spaceships, we can change it into just 3 functions. Again, like, don't spend too much time looking at this. Just note the difference between wall of text and the somewhat smaller wall of text. But this is 3 functions. It's a lot easier to reason about because you can actually like almost see it on a slide, right? We don't have to maintain all of the code we had to do before. We don't have to write all the code we have to before. So in the cases where you have to write your own comparison operators, this helps. And in the case where you can just let it be equals default, then it's great too. And so we've gone from being unsurprising, but with a ton of code, and now we're just unsurprising. This is a big win. This is C++20 helping us solve problems which we previously could not solve very well. And this is going to be kind of a theme for the talk. Noexcept propagation. So the kind of golden rule of Noexcept is if you do one thing, just make sure you propagate, you care about the Noexceptness of your move and swap operators. Because people are going to be checking these and optimizing based on whether one of these operations can throw. So as a demonstration, say we have a vector of optionals, and this optional is storing just so this tracer thing just traces when it's copied and moved and assigned and things like that, just so I can get some numbers out. So if we do not propagate the Noexceptness of our move constructor, then we get over 200,000 copies and 100,000 moves. But if we do make sure that if our underlying type is Noexcept move constructible, then our wrapper is, then a bunch of those copies now become moves. And depending on what the stored object is, if it's very, very cheap to move and very expensive to copy, like a vector or something, this can be a huge performance gain. So we really want to think about this when we're designing our types. If anything, just think about your moves and swaps. That's all I ask. So this is not performant. But there is something we can do. This is what a copy constructor for an optional might look like. It checks if the other one has a value, and if it does, then it will construct the value held in our current optional. And otherwise, it just sets that I do not have a value. So what we can do is in the signature there, we can write a Noexcept specification. So this is a constant expression Boolean, which you can put inside Noexcept, and this says, I am Noexcept depending on the value of this bool. So in this case, I am Noexcept if my underlying type is no throw move constructible. And so this will be worked out at compile time. And now we've propagated the Noexceptness of our move constructor. And you can do this for anything. You can put any arbitrary expression in this Noexcept specifier as long as it's a constant expression and converts to bool. So now we're performant. And there's not a whole lot better we can get than this. I don't really want to get into Noexcept auto, which has been proposed and shot down a number of times. But this is not so bad. So I'm quite happy with this as it is. We don't need to go and look for more improvements there. This is a quote you may be familiar with. Too explicit or not too explicit? That is the question. And that's what I'll be answering next. So say we have our very simple wrapper again that you saw at the start of the talk. If we try to initialize a wrapper of int with an int like this, we get a compiler error. This seems like a reasonable thing to request, right? I have a wrapper of ints. I want to store an int in it, so I just write equals 0. This should compile. So maybe what you're thinking is, oh, I'll just write a constructor. It'll be great. And now the smarter ones are saying, ha, I know, we can use perfect forwarding. It'll be great. But then someone comes along and they write this very, very aptly named type. Oh no. So note this has an explicit constructor from bool, And presumably someone has written explicit there for a reason. They haven't just like slipped and accidentally typed it. They thought about their type design. They thought, I want to be constructible with a bool, but I don't want it to be implicit. That would be bad. So now we can write a function which takes a wrapper of oh no's. And because our constructor, which we defined up here, is not explicit, then we can just pass true, and it implicitly converts. So even though the type designer for oh no said, don't allow implicit conversions there, we've just like ripped the rug from under their feet and said, oh, this is fine. Oh no. So this is surprising. We don't want this. So what we can do is we can use some enable if magic. Is anyone here not familiar with enable if? Okay, I'll give a very quick introduction. Essentially, this says if these expressions, this is convertible and is constructible, evaluate to true, then this is fine. You can call this function. If they evaluate to false, then the function is essentially like removed from the candidate set. It's just discarded. We don't think about it. We can call some other function if it exists. This is S-fine, substitution failure is not an error. So what we can do is we can have two overloads. One, which is not explicit, as in the comment there, and one which is explicit. And the only thing I've changed here is this this is convertible condition. See, I've just added an exclamation mark there, and there's not one there. So the only difference is if there is an implicit conversion from U to T, we want to maintain our explicitness, essentially. If the conversion is implicit from our underlying type, we want to be implicit. If it's explicit, we want to be explicit. And now we compile. So we're no longer unsurprising in that case, nor this case. We now can no longer implicitly convert this true into our wrapper of oh no's. So unsurprising, but we have code duplication. So we had to write the same function twice, and literally the only thing which we changed was that exclamation mark and the explicit. And as we all know, we don't really like code duplication. It means we have to maintain both of these functions. We need to write both these functions. It's a headache. We don't want it. So we have Noexcept bool, as I showed you in the Noexcept propagation part. Maybe we could have explicit bool. You know, something which takes a constant expression bool and says, I am explicit if this is true. If this is false, I am not explicit. We can have an implicit conversion here. This seems kind of nice. So we can go from our two overloads where we had our explicit and our non-explicit. And the only thing which changed was the is convertible. So we can just move that down into this explicit specifier. And now we have one overload where we previously had two. Does this make sense? So this is actually in C++20. I'm not sure if it's implemented any of the major compilers yet, but when it is, you can go ahead and use this and get rid of your code duplication. And then that can take us from being unsurprising with code duplication back to just being unsurprising. So this is, again, C++20, making our code better. Conditionally deleting special members. So this is part of the talk where we, if we're looking at one of those old style maps of Britain, this is the part where it would say, here be dragons. So we're starting to get into some weird tricks which standard library implementers, boost implementers all have to think about, because this stuff starts to matter and you get very weird behavior if you do not follow these. So this is a very, very simple optional implementation. It's essentially a union of either we're a T or we're nothing, and nothing is expressed just with a dummy character type. And then we have a Boolean to say whether we're engaged or not, whether we store a T or not. So we can write a copy constructor for this. which is pretty much what you saw earlier, just checks if it's engaged and does a placement new. And we can write a destructor for it, which checks if it's engaged and destroys. But the problem here is that these two functions are defined no matter what the underlying type is. So if the underlying type does not support this or this, then we start to hit problems. So as an example, this is a not super important reason to do this, but if you think about having an optional of unique pointers, like you cannot copy unique pointers, so you cannot copy optional unique pointers. Makes sense. So if we conditionally delete our copy constructor, we get better error messages. So in the first one, you can see it says, we have a call to deleted constructor of unique pointer in this kind of internal placement new thing, which really shouldn't really be exposed to users. And then in the second case, it just says, oh, the optional unique pointer constructor was deleted, and here's where you tried to use it. So this is just one of those kind of nice quality of life improvements where it makes our error messages better by doing this. But an even more important reason is, yes, I just wanted to draw attention to this. This is on line 2299 of my optional implementation. This is an object which is either a type or it's nothing. 2,000 lines. Yeah. This is the problem that we have to face with C++ today. But say we want to check at compile time if option pointer is copy constructible. This is what we want to do if we're building like other types on top of this. If we're doing some meta programming to work out how to handle this type. These are the kinds of things which come up all the time in generic libraries. Now, problem is, if we don't actually do some work, we get the wrong answer. So if we do not delete our copy constructor when it doesn't exist, then this trait is going to tell us, oh, this is fine. You can copy an optional unique pointer, it'll work. But then when you actually try it, then you get a hard compiler error. And you can't do things like the trick I showed earlier with enable if. You can't get rid of the candidate and go and do something else. No, the compiler just says, you tried to do something like totally illegal. So we're just going to shut down. You cannot recover from this. So this is why we need to care about deleting our special members, because it's surprising. So one thing we could do is we can take our optional implementation and we can make it a base class. Then we can make our actual optional type, and we can inherit from our base class, and we can inherit from these special things which are going to magically delete our copy constructors and our assignment operators. And there's kind of no way to get around this. You have to do it by inheritance just because of how the rules of special member functions work. And then the implementation of these delete CTOR base gets very hairy. Essentially, you need to say, okay, I'm going to check if copy is allowed, and I'm going to check if move is allowed. Then I'm just going to define a bunch of defaulted constructors and assignment operators. So I can spend a little bit of time on this because it's a bit weird, but essentially you have, if my underlying type is both copyable and movable, then I default both of my copy and move constructors. If it's true and false, then I default and I delete. False, false, delete, default. I'm just covering all of the cases. Does this make sense? Does anyone have any questions about this stuff? No. Okay. So you have to write all of this, and as you can see, we have like 4 classes which are kind of not really doing anything. We're just deleting and defaulting member functions, and we have to write this just so that we can get the behavior we desire. And then we need to do exactly the same thing with the assignment operator, and that will have 4 more cases. It just becomes such a mess. We don't want to do this. But now we compile. If we say, I'm going to assert that we cannot copy an optional of unique pointer, and it'll say, correct, you cannot copy an optional unique pointer. So we're back to being unsurprising, but it's a ton of code again. Maybe sensing a pattern developing here. So what we could do is use concepts. An interesting thing about concepts is not only can you constrain templates, but you can also constrain non-templates. You can constrain normal functions like this. So I can say that my copy constructor requires that the underlying type is copy constructible. And if it's not, then this thing will not exist. And this is essentially the equivalent of doing our mess of multiple inheritance and writing all of these classes, which did essentially nothing except tell our compiler what we were trying to do. So this is a huge win in terms of the amount of code we have to write. So we've gone from being unsurprising with a bunch of code back to being unsurprising. Triviality propagation. How many people are actually familiar with the idea of triviality? Handful. So we'll go to the Holy Tome, the sys5 ABI. This is the document which kind of specifies on a given system using this ABI, such as Linux systems, how things are actually done at the binary level. Like, how do binaries communicate with each other? How can you call a function? What's the calling convention? So this is where we can look to see what triviality will really, really mean for us down at that level. So it says, an object with either a non-trivial copy constructor or destructor cannot be passed by value because they must have well-defined addresses. So to dig into this a little bit, it's not quite C++ passed by value, because we can pass these things by value in C++. It's more talking about, can I pass this in registers? Because passing in a register is a copy. You're taking the data from the stack or another register, and you're putting it into the register, which the calling convention says, here's where arguments go. So that is a copy. And if things have non-trivial copy constructors, then we cannot do this. And this becomes important. So just a kind of quick description of what triviality really means in the sense of C++. A copy constructor is trivial if it's defaulted or implicitly defined, and it has there are no virtual member functions or base classes in the class for this constructor. And if all of the base and member copy constructors are also trivial. So if you have a class which just has a std string member, then that's not going to be trivially copyable because std string is not trivially copyable. Does this all make sense? Cool. And then trivial destructor is very, very similar. Has to be defaulted, implicitly defined, not virtual, and the destructors for members and bases are also trivial. So we have this static assert here. Is my optional trivially copyable? This will be a compiler error if we have not actually done some work, very similar to the special member deletion. If we don't do the work, we don't get the benefits. Very similarly for trivially destructibility, we don't get it by default, even if int is obviously trivially destructible, right? You just don't have to do anything. But our optional event is not. So this is not performant. And maybe it's not entirely clear why, but I'll show you some assembly listings. So say we have a function called get42, because of course, you want to get 42. It's going to return an optional, and this is what the assembly looks like. So if you're not familiar with x86, don't worry, I'll explain. Essentially without propagation, we're having to put this thing on the stack and then pass the address of it to the function. Like we're returning an int here, essentially. It's an int and a bool to say that we are storing an int, but we're essentially returning an int, and we're having to go to the stack. So if you're calling functions like this really often in a tight loop or something, this kind of stuff starts to add up. We're having to go to our stack more often. We're clearing out cache space that other things could be using. We're not using our registers effectively. These like very small things start to make a difference. And it gets even worse if we look at other cases. So if we, instead of returning an optional, we're taking an optional as an argument. This is the same kind of thing. We have to put it on the stack. In this one, we're literally just putting the representation of this object in a register and calling the function. And because it's tail recursive, we're just doing a jump. Since it's a tail call, we're just doing a jump. We're not even having a call instruction. And these things start to pile up even more. And then even worse if we don't propagate the trivial destructibility, because then the compiler has to do more work. And it's even worse if we have a vector of these things. Like this is a vector of ints, and we're emitting all this code for it. I mean, it's not like quite as bad as it first looks. It's essentially just an unrolled loop. But like the code size here starts to matter for instruction cache performance and all this stuff. So this is bad. We don't want this. For vector of ints, no. So maybe what a lot of people say is, okay, fine. I've seen enable if, I know what I'm doing. I'll just take my destructor and I'll put a bunch of magic on. Happy. If t's trivially destructible, then we'll just get rid of this this overload, and the compiler can just do nothing. But doesn't work. How many people were in Walter's talk just before the session? Handful of people. So just like Walter said, special member functions cannot be templates. Copy constructors cannot be templates. It might look like a copy constructor, but it's not. And you cannot do enable if on things which aren't templates, so it doesn't work. So what we have to reach for again is private inheritance. This is the kind of stuff, you look at a standard library or a boost library for the first time, you're like, why is there just private inheritance all over the place? Isn't this like, don't we say not to do this stuff? And it's for reasons like this. There's literally no other way to do it. There's another way. Tell me your other way. Sure, you could do that. Yes. Yeah, so Arvid's comment was you could do it another way by having a trait which selects a type to change out for the storage. But it's essentially just swapping the inheritance for composition. You're doing the same thing at the end of the day. So what we can do is we can have a storage base for when we are not trivially destructible and we have to call this destructor. Like if we do not call this destructor, then bad things will happen, like we'll leak memory or some other resource, and someone will be not very pleased at us. So we want to call this destructor when we have to call it. So this is the version for when, yes, you have to call this destructor. And then if the underlying type is trivially destructible, then we just default our declaration and say, just do nothing. It's an int, you know, you don't have to call a destructor. So now we have to have this extra layer of indirection, which is telling us whether to have a destructor or not. We're splitting our definition of our class because suddenly our destructor can't live in our actual optional implementation. It has to live in this weird base class. So we have a bunch of problems here. And of course, we then have to do it for the copy constructor, and for the move constructor, and for the copy assignment operator, and for the move assignment operator. Isn't C++ just fantastic? So I'm sure that none of us want to do this, especially because at the end of the day, you essentially just privately inherit from this last one. You inherit all the way up the chain, and then you just default your destructor because your base classes are going to deal with doing all the actual work. So now this compiles, and this compiles. So we're performant, but a ton of code again. So what we could do is use concepts again. We say we have our destructor. We have a copy constructor, which if the underlying type is trivially constructible, then we just default it, and otherwise we do some work. It doesn't quite work with concepts as they are now. We need like a extra bit of wording to say, oh yeah, if this copy constructor is not valid, then triviality is preserved. There's just some weird standards wording issue there. So there is a paper P0848, which is hopefully going to get moved on in Kona at the next standards meeting. So hopefully we'll get something like this in C++ 20, and we won't have to deal with all of that mess. And all of this would bring down my optional implementation from like 2,000 lines to a few hundred or something. It's a huge difference. And so obviously we've gone from being performant with a ton of code to being performant again. How do you know if a C++ developer is qualified? Anyone? You check their CV. Another possible answer, check their references. That's what I'm going to talk about today. Ref qualified accessor functions. If we have a deref operator like this is something you might have in an optional. It just gets your stored value. Might be called get, might be called value. So it's just one possible spelling of it. It's very, very common to see this kind of pattern. You have a non-const version and you have a const version. Because when the wrapper is const, you want to propagate that through. You don't want someone randomly just doing undefined behavior. That's bad. And we want it to work with non-const objects as well. So we have to write both of these overloads. Quiz. Do these move or do they copy? Anyone? First copy, second moves? First copy, second moves. Yep. So the first one copies because we move the optional and then we dereference it. But our dereference operator doesn't care if this is an L value or an R value. Like, we haven't done any work to actually propagate that through the call. So it's just going to end up with an L value and we copy. Whereas in this case, the second case, we deref first and then we move. So we have an R value. So this is not performant or unsurprising, because we might accidentally copy, and like this mismatch just doesn't make sense to a lot of people. So what we can do is, instead of having 2 functions, we have 4 functions. And we write these ref qualifiers. So these first 2 will be called if, well, the first one will be called if the object we call this function on is a non-const L value, and then a const L value, non-const R value, const R value. This has been in the language since C++11. It's not used a whole lot by a lot of people, but it really makes a difference for things like this. This const star value is very weird as well. Walter, I think, in this talk said that he pretty much has no use case. I have one use case. So std cref, which gives you a const reference wrapper, has the const ref version deleted so that it protects you from trying to make a reference wrapper to something which is going to die, and you get a dangling reference and undefined behavior. So without const ref, you get whatever your favorite undefined behavior metaphor is, and if you have const ref, then you just get a compiler error. So this kind of stuff saves you. It's an edgy case, but sometimes these things matter, and this would take ages to find. Like undefined behavior because const ref is not being handled by your library. That's going to be a pain. But back to having the 4 functions. We are now performant and unsurprising, but again, well, code quadruplication even in this case. So we can do deducing this. So this is a paper which I have co-authored with Barry Revson and Ben Dean and Gashbert Asman. Maybe C++20, looking more likely C++23 at this stage, but we'll see how we go. Essentially what this allows us to do is, instead of writing overloads for all of the different cases, we just deduce what the type of this was. We deduce whether it was an L value, whether it was an R value, whether it was const, even whether it was volatile if you really care. So this one function is essentially the equivalent of all 4 overloads we previously had. If you have any more questions about this paper, you can come talk to me afterwards. But I really hope that we get something like this. It just clears up so much code and helps us go from performant and unsurprising, but with code duplication, and gets rid of the duplication. S-fine unfriendly callables. So this is the last part of my talk. And this is the part where, if we were on that map again, and it said, here be dragons, we've gone in and we've stumbled upon that little copse where the dragons don't just breathe fire, they breathe other smaller dragons, and they also shoot lasers out their eyes, and everything is just terrible. So this stuff is has been brought up in committee meetings, and we're thinking about how we can actually deal with it. But it's some difficult stuff, so I will try and go slowly on this, and please stop me if you'd like me to explain some more. So say we have our wrapper again, just a wrapper of T, starting off nice and easy. Now we have these 2 functions. They're called pass2, and they take something which is callable, like a function, a closure, a function object, whatever. And then it calls that function with our stored object. Okay, does that make sense? We're just taking a function and we're calling it with our stored object. And now we want to have overloads for non-const and const because this might matter to the function we're calling. So we have to have our 2 overloads again. So now for a use case. Say we have a class called foo with this dothing function. Our function is non-const. Important to remember. And we have a wrapper of foos, and we try to give it a function which calls dothing on our stored object. So just to be clear, this f gets this function object and is going to call x.dothing on its stored object. Does anyone have any questions about this code? No. Okay. This compiler errors. And it says, passing const foo as this discards qualifiers. where is the const? No, this isn't const. The lambda, if it captured by value, sure, the call operator would be const because we haven't put mutable in there. But there's no instance of the word const in this code. Yet, our compiler error is saying you're passing a const foo to this lambda. What are you doing? So this is surprising, and the reason is the const is here. So the const is on the member function passed to, even though our wrapper of foo is not const, somehow this const is making its way into our lambda and causing us issues. And so what actually happens is these function signatures have to be looked at for purposes of overload resolution. So when the compiler is saying, do I call the const version or the non-const version? I don't know yet, I'll check. So the compiler checks this decal type and says, oh yeah, this seems legit. And then it checks the other decal type, which means it has to pass a const foo to this function. And that doesn't compile because our do thing is not const qualified. So essentially, overload resolution is stopping our code from compiling because the machinations by which overload resolution work happens to make this const go into context where it breaks our code. And there's literally fundamentally no way to solve this in C++ today, which is a real pain. I had a bug report for almost exactly this use case for my optional library. I spent days trying to work out what was going on here till I just asked on Slack and someone's like, oh yeah, I wrote a paper about that. It's really weird. Pardon? Yep, because this thing is not an SVNA context, you can't like just have a soft failure where we get rid of the candidate set. When it tries to instantiate this lambda, then it fails inside the body, and so it has to have a hard compiler error. So it turns out, oh, where are we going? So what we could do is we could remove these decal type expressions, and this does work, but it changes things very slightly because now if we're trying to do more SVNA stuff, then these things are not SVNA friendly, and these can cause us more hard compiler errors. And the whole thing is just like compiler errors all the way down. So now if we get rid of the decal type, then this will compile, and it will be fine for some definition of fine. And now we're unsurprising, but we're no longer SVNA friendly. So it turns out we accidentally solved this problem with the Deducing this paper. It turns out making this thing a template and deducing whether the object you call it on is const qualified or not const qualified solves this problem. Because suddenly you're not having to perform overload resolution with const and non-const versions of the member function. You're just deducing it, and the const version was not even considered. But if you don't pass a const foo, then there's going to be no const anywhere. So we kind of solved this by accident, and hopefully we can get this fixed into the standard. And that'll take us from no longer being SVNA friendly to being unsurprising again. So thinking back to the start where we had this comment in the code, hopefully I kind of equipped you with some ways where you can think about if you see these things yourself in your own code base or a code base you're using, you can come back to this talk and say, oh, maybe I can apply some of these things which I talked about today. Comparison operators, triviality, propagation, all this good stuff. And that is how to write well-behaved value wrappers. Thank you.